For today's lecture, we're going to be talking about textural and chemical sediment maturity. And by the end of this lecture, you should be able to answer the question of how do we go from mountains made of granite and other rocks to beaches that are primarily made of quartz sand. What are all the processes that get us from our parent rock all the way down to the sediments that make up the sedimentary rock that we care about in this course? So as we've talked about already, you know that sedimentary rocks are made from pieces of other rock. Those sedimentary rocks that are closer to the source tend to be larger in grain size, and the farther we get away from the source, we tend to see a decrease in grain size, all the way down to our silts and clays that tend to be deposited out in the deeper parts of the ocean. So clastic sediment, clastic being the clasts, the individual grains of sediment, forms from weathered rock. And what we're going to talk about today are some of these weathering processes. In petrology, we go into great depth to understand all of these weathering processes. And so today, I'll just be able to provide you with a brief overview of what processes and aspects of the rocks and minerals themselves control this weathering process. So, in terms of what controls weathering, we have a variety of controls, and so we're going to walk through those really quickly. The first is what the original rock is made out of. What is the mineral stability? So you can see in this chart that the most stable minerals at the Earth's surface are things like iron oxides, aluminum oxides, and quartz and clay minerals, and the least stable at the Earth's surface include things like halite, calcite, and olivine. And this chart may look familiar to you because it reflects the Bowen's reaction series. So in Bowen's reaction series, olivine and pyroxene are some of the first minerals to crystallize at high temperatures. So this is their happy place at high temperatures, their equilibrium state. But at the surface, at the relatively low temperatures of the Earth's surface, they're going to break down. This is in contrast to things like micas, feldspars, and quartzes that crystallize out at lower temperatures, about 600 degrees Celsius from our igneous melt, and therefore are more stable at the Earth's surface. So this chemical mineral stability diagram follows a lot of this reaction series, from our olivines through pyroxenes, micas, down to quartz. Another thing that controls how a rock weathers is the parent rock type, the rock fabric and the texture of that parent rock. So rocks that have fissile layers, that have joints or fractures, that are exfoliating like the granite of Half Dome, or that show foliation like the schist, are going to be places, weaknesses in the rock, where weathering and erosive processes can take place. So the more sort of fractures or layers in your rock, the more weathering can take place. Another thing that controls weathering is your climate. So places that have wetter climate, where there's more rain, there tends to be more chemical weathering. So all of that moisture, the water itself, interacts with the mineral, maybe to dissolve the mineral, to carry acids to the mineral, or oxygen to the mineral, to induce chemical reactions, versus dry locations, which will have less rainfall and therefore less chemical weathering. And then temperature. So temperature speeds up chemical reactions. So places that are warm are also going to tend to have increased weathering rates. This is in contrast maybe with a glacially dominated system, which is cold, but the glaciers themselves, the physical processes, do contribute a substantial amount to weathering. The amount of soil can also control your amount of weathering. If it's thick, it's going to be a blanket over the sedimentary or other rocks, and so inhibit weathering to some extent. A thinner absent soil means the rock is closer to the surface and more prone to weathering. So here are some depictions of soils, ancient soils in the rock record. How long the rock has been at the surface, of course, also controls how much weathering it's experienced. So here is a very famous rock that has been out at the surface for 600 million years, a very long time in terms of Earth history. So it has a lot of exposure and a lot of time to experience weathering. Versus this relatively young rock down here, another set of famous rocks, that have only been at the Earth's surface for about 10,000 years, and so have not undergone as much weathering. Tectonic events will bring rock up toward the surface, so it provides new rock at the surface to weather. And the physiogeography, or the topography, controls how much gravity there is to contribute to physically disaggregating our particles. And the other aspect of physiogeography has to do with the presence of other physical weathering forces, like pounding waves or blowing winds, that are going to be enabling grain-to-grain contact that will further weather the rock. In addition, the amount of moisture in wet environments is also going to contribute to that chemical weathering process. So we already have this general sense that as we move away from the source, the rock that becomes our sediments becomes more rounded and finer grained. Because of all those grain-to-grain interactions, those are breaking off the angular edges of our grains, the grains become more rounded. This sorting happens because fast-moving water is carrying away different particles, and so our larger particles get left behind closer to the source, and the finer particles get carried farther and farther away from the source. So the process begins here. And the first thing that's going to happen is you're going to be removing your clays. Those are going to get carried away downstream or out into the ocean. So then you're going to have the sorting of your non-clay portions, so the sorting of pebbles and granules and sand and silts, and then the rounding of grains. It takes a very long time to round all of your grains. So we break up the textural maturity into these four classes: immature, submature, mature, and supermature. So an immature sediment is going to have a lot of clay, poorly sorted grains, angular grains, and so you know that this rock is probably found pretty close to the source. It's texturally immature. Compared to a supermature sediment or sedimentary rock, where there's little to no clay, the grains are well sorted, which means that all of the particles are of a similar size. The grains are rounded, and we know that we have experienced a high degree of transport and weathering processes, both chemical and physical. So we'll be using the amount of clay, the amount of sorting, and the amount of rounding to describe the textural maturity of our rocks. In addition to textural maturity, we're also interested in chemical maturity. So now we're going to talk about some of the chemical processes that break down, physical and chemical processes that break down rocks. So we have two modes of weathering. We have physical and chemical weathering. Physical weathering includes things like freeze-thaw, where water gets into the cracks of rocks, expands when it freezes, and breaks the rocks apart. The same process can also happen with tree roots, which will enter into cracks in the rock, and as those tree roots grow and expand, they further crack the rock apart. Another example of physical weathering has to do with how rock surfaces heat up and expand under solar conditions, and then at night, as the rock cools, it contracts. And all of that expansion and contraction breaks the rock apart, and all of those cracks then become surfaces that are then exposed to more physical and chemical weathering, and breaks down the rock into smaller and smaller pieces. A somewhat similar process is stress release, where as rock is being pushed up to the surface, the stress is relieved from that rock, it's no longer buried, and we start to see fracturing of that rock as it's able to expand a bit. So similar to the expansion that we were seeing in solar insolation, the release of stress of overburden of other rocks and bringing this rock to the surface allows it to expand and crack apart. And again, those cracks become areas where water, roots, and chemical weathering can take place. So here's an example of stress release. You'll see this in Yosemite. You see this happening in the rocks in Joshua Tree National Park as well. The final aspect of physical weathering is tectonic uplift and wind and water. And this is last on the list on purpose. Most people, when you ask them what contributes to the physical weathering of sedimentary rocks, are going to say wind and water. That's going to be the first thing that comes to mind. But it probably actually has the least to do with the actual process of weathering rocks. When you think about it, water is not that strong. It's not that dense. It tends to flow around sedimentary rocks and other rocks. And so what's really happening is that water is able to carry other sediment particles that can bang into our rocks. And so it's that grain-to-grain interaction that is facilitated by flowing water or facilitated by blowing wind that actually does the physical weathering of the rock. But the processes we've already talked about, like ice wedging, root wedging, insulation, expansion and contraction, and stress release are actually going to be more important for our physical weathering processes. So this example is, of course, of a canyon, and you might think, oh, this river has run down this canyon and slowly eroded grain by grain these sedimentary rocks to form this canyon. But instead, it's probably the root wedging and the ice wedging and the insulation that's actually bringing down larger particles of rock that are being then carried away by that water. Another really important aspect of weathering is chemical weathering. So chemical weathering has a couple of different reactions, and in petrology we go into the details of these reactions. Here I just want you to be familiar with some of the opportunities, the different ways that rocks can be chemically weathered. One of those is simple dissolution in water. So for example, here is our sodium chloride. This is a sample of halite or salt. And of course you know that salt can just dissolve away in water. So it's really easy to break down halite with just exposure to a little bit of water. Versus something like quartz, which is SiO2, so here's our quartz, piece of quartz rock. In water, you probably have the idea that it's not exactly soluble. Our beaches aren't exactly dissolving away, right? So our sodium chloride, our halite, our salt is much more soluble in water than quartz. So different minerals are going to react differently with reactions with water, with simple dissolution. But most water is not a pH of 7. A lot of water contains a little bit of acid. That acid is picked up from the scrubbing of clouds as acid rain. So we have carbon dioxide and water in the clouds reacting to form carbonic acid. Sulfuric acid and water in the clouds, and nitric acid formed by reaction of nitrogen gas in the clouds. And so all of this pollutant material that we put up into the atmosphere, and that also is released by natural processes like volcanic eruptions, contributes to making rainwater and therefore groundwater slightly acidic. And you know that acids are then going to accelerate weathering. Here in particular is a statue that has been weathered by acid rain. Another process, probably one of the most important processes for the chemical weathering of rock, is hydrolysis. So even though the word hydrolysis sounds like it has something to do with dissolution or water, it's really a process of interchanging the ions that are in the rock. So in hydrolysis, a hydrogen ion that is present in the water is able to interact with the cations that are in the mineral. And so this process is particularly important because it is the process that weathers most silicate materials. Most silicate minerals chemically weather through this process of hydrolysis. Olivine and pyroxene can be completely destroyed by hydrolysis, and feldspars will dissolve partially and produce clay minerals. So for example, feldspar will undergo a hydrolysis reaction to form a kaolinite clay, and that kaolinite clay can undergo a second hydrolysis reaction whereby gibbsite is formed. So I'm not too concerned with you remembering exactly What is happening at the chemical level here, that was more part of the petrology class, but just the idea that there are these reactions where ions are being interchanged between water and between the mineral that causes the breakdown of minerals over time through this chemical weathering process, hydrolysis. And that this hydrolysis process is actually more important than simple dissolution with water or even acidic dissolution with water. Hydrolysis is what's breaking down the greater proportion of our silicate minerals at the Earth's surface. So here's an example of feldspars getting weathered to kaolinites. So these are feldspars within a granite. You can see here the sort of vitreous luster of the feldspars, and over here they become quite dull. So over here, all of those feldspars have turned into kaolinite through that hydrolysis process. Another important chemical weathering reaction is oxidation. In oxidation, an oxygen molecule is reduced and the mineral becomes oxidized, aka it is rusted. So oxidation is defined as a loss of electrons, and reduction is defined as a gain of electrons. So effectively, oxygen is stealing electrons away from the mineral, and that mineral then becomes oxidized. So pyroxene is one particular mineral that will undergo oxidation to then form an iron oxide, and we see a lot of oxidation happening when we are looking at outcrops of older rock that have turned a sort of pinkish or reddish color. That has more to do with this iron oxidation than it has to do with the original color of the mineral that's making up that rock. So let's come back to this chemical weathering stability diagram. We've talked about a lot of different processes that physically weather and chemically weather rock. And now that you have some understanding of those processes, you might look at this diagram and have a good idea of why things like iron oxides and quartz and clay minerals are the most stable. Because those minerals either don't react with acids or undergo hydrolysis or oxidation reactions, or they're the end product of those reactions. So iron oxide is the end product of oxidation. Gibbsite is the final product of two hydrolysis reactions. Quartz is relatively non-reactive, and clay minerals are also the last product of some of these hydrolysis reactions, as well as being some of the smallest physical particles. And then on the other side of this chart, something like halite is most reactive at the Earth's surface because it is easily dissolved in water. Calcite dissolves very easily in water with some acidity, and olivine is going to break down through that hydrolysis reaction, as does pyroxene. So now you have some understanding of why minerals are aligned in this particular order in terms of their stability. So in summary, for our weathering processes, the amount of exposure that you have leads to more physical and chemical weathering. Our mineral stability controls where you fall on the framework of more stable minerals with less weathering to less stable minerals with more weathering. Increasing temperature increases weathering reactions. More rainfall means more water, so more opportunity for chemicals to be brought into contact with the mineral surface, things like acids or oxygen, to undergo these hydrolysis, dissolution, and oxidation reactions. More acidity, again, is going to result in more chemical weathering, and however steep your slopes are, that's going to lead to more physical weathering as gravity is pulling the sediments down into the valleys. So the other aspect of understanding where a granite gets turned into a quartz sand has to do with understanding how all of those processes we've just talked about, the physical and the chemical weathering processes, sum together to make the sedimentary rocks that we see at the Earth's surface. So our quartzes we have broken down sedimentary rocks into three basic types. Those that are dominated by quartz, those that are dominated by feldspar, and those that are dominated by lithic fragments. And you'll see, particularly over this lithic fragment, it says unstable. So these tend to be all of the other minerals that fall on that unstable side of our mineral stability chart. So things like halite, calcite, olivine, pyroxene, even some of our micas are all going to be found in this lithic fragment column. Versus quartz, which we know is very stable at the Earth's surface, and feldspar relatively stable, but not as much as quartz. Quartz is appearing at the top of this chart. That can help you remember that quartz is one of the most stable minerals at the Earth's surface. So this diagram helps us understand where we might expect to find an abundance of quartz sediments. And so what this figure is showing is the shift in mineral content as we move from a rock that was found in a fluvial system, a river system, toward a beach system. So each of these arrows represent a particular river that dumps out onto the beach, and what we're looking at is the chemical change in the mineral content of the rocks. So these are connected fluvial to beach systems. So if you look at the sediment, for example, in river number 5, it tends to be mostly made out of lithics. But by the time that sediment is transported to the beach, it tends to have a greater quartz contribution because we're moving up in this ternary diagram, and is moving more towards the feldspar contribution. We're moving to the left in this diagram. The same goes for river number 3, where we're greatly increasing the amount of quartz and a little bit more the amount of feldspar. River number 12, again, going up in the amount of quartz and a little bit more feldspar. So we're effectively losing the lithic component in each of these river to beach scenarios. The amount of quartz is increasing in each one of these, and a little bit the amount of proportion of feldspar is also increasing in each of these. We're not making more feldspar or more quartz, we're just removing lithic fragments. So in each of these scenarios, as a river runs through its course and makes its way to the beach, lithic sediments are being lost. So what's happening to those lithic sediments? Well, they're undergoing some of those physical and chemical weathering reactions that we've talked about. They're being broken down by hydrolysis, being broken down by oxidation reactions, by dissolution, and so as the river is running, we're losing more and more of these lithic fragments. Then finally, this sediment makes its way to the ocean and is now extended along a beach. And at the beach, those grains, those individual pieces of sediment, are experiencing a lot of physical weathering from the grain-to-grain interactions that take place with every breaking wave. So they're breaking down physically these softer minerals, which remember quartz is quite hard. It has a mineral hardness of 7 out of 10. So again, we're keeping the quartz, but we're breaking down any of the physically softer minerals, and we're still in a wet environment. So we still have all of these chemical reactions taking place. So at the beach, this is basically a great sediment weathering factory where we have high rates of physical disturbance and chemical disturbance that's leading to the breakdown of both lithic fragments and our feldspar minerals. So all of these sediments are driven to be more proportionally rich in quartz over time. So we can use the amount of quartz, feldspar, and lithics to determine the source rock and the weathering process that has brought the source rock to be the sediment that we see. So we can look at the proportion of quartz, the proportion of feldspar, and the proportion of lithics to plot a sedimentary rock on this diagram. And I asked you to do this for the field trip. If you see a rock that's made of more quartz than any other sediment, more quartz than feldspar or than lithics, that rock tends to have come from the continental interior, someplace where a lot of weathering has taken place over hundreds of millions of years, but no new rocks have been introduced. So rocks have been breaking down through physical and chemical weathering processes, where we now have predominantly quartz. All of the other minerals have been eroded away to clays, which have then been transported away by running water, and all we're left with are these quartz grains. This is in contrast with a rock that is really rich in lithics. Lithics, again, are going to be chemically and physically reactive, and so we know that we have a rock with a lot of lithics in it, that it has to have been more recently eroded from a magmatic arc, because it's going to have more recent sedimentary rocks, things like cherts, and other sediments from the ocean floor, and it's going to have volcanic rocks from that magmatic arc system. And then as we move to have a greater concentration of feldspars, that's indicative of some kind of basement uplift. So more ancient crustal rocks that are being brought up to the surface are going to tend to be more rich in feldspars. The lithics have been eroded away, but it hasn't undergone so much erosion to form a more quartz-rich rock. It's undergone just some moderate amount of weathering, and so when we bring that rock back up to the surface, it tends to be rich in feldspars. The composition of that rock also makes it more rich in feldspars. So places that have had old mountain belts will have more metamorphic activity, which will be creating some of these concentrations of feldspars. And the interior of plutonic igneous rocks, which have not yet been brought up to the surface, will also tend to have more feldspar. So the source rock itself tends to be very feldspar rich, and then we're bringing it up to the surface. So just to recap, we're going to find more quartz in beaches and in desert environments where there's been a lot of physical and chemical weathering, removing all of the other lithics and feldspars to primarily concentrate the quartz. Feldspars we're going to get in regions where we have a lot of relief, so a lot of steep topography, because you need to erode the sediment before that feldspar starts to break down to clay. If that feldspar gets carried down a river, it's going to break down to clay through that hydrolysis process. So we tend to see feldspars in fluvial settings, that's rivers, alluvial settings, which are our alluvial fans, like you saw on the field trip, and places that are generally close to the sediment source, because the farther that feldspar has to travel, the more likely it's going to get broken down. We also sometimes see feldspars in the desert where there's less chemical weathering taking place and it's less likely to get turned into clay. And again, the source of these feldspars are going to be basement rocks, things that have been buried deep in the crust and have undergone metamorphic processes, or are the remains of the interior portions of magmatic arcs that are going to be more feldspar rich. So when those are brought up to the surface, those become our source of feldspars. And then for our lithics, these are going to tend to be formed from younger rocks, from magmatic arcs. Those magmatic arcs are being attached to the continent, and they are bringing magmatic material as well as ocean sedimentary material up to the Earth's surface to be then eroded away. So there'll be low-grade metamorphic rocks and a lot of volcanics making up your lithic fragments. We commonly find these in fold and thrust belts and in continental blocks. And in general, we'll find lithic fragments concentrated in fluvial deposits, again, because the farther these rocks get transported, the more likely they are to break down. And we'll also find lithic rocks in turbidites, which we talked about, those submarine density flows. So just to bring us back to the beginning here, we talked about the textural maturity of rock, the idea that the amount of clay, the amount of sorting, and the amount of rounding when we're observing our sediment texture can tell us something about the maturity of the rock. And then we've also learned about the chemical maturity of the rock. The amount of quartz, the amount of feldspar, and the amount of lithics tell us how long that our sediments have been exposed to the Earth's surface and the types of weathering processes that they've undergone. So what I want you to do is to look at this particular figure and answer the question, can you use what we just talked about in terms of mineral stability and weathering processes to explain the distribution of minerals and sediments in the size classes in which they're plotted? So for example, we can look at our feldspars and we can see that the proportion of feldspars tends to form within the sand and silt-sized region. Why is that? Why are there no feldspars the size of clay particles? And why are there tend not to be feldspars much larger as gravel-sized particles? What about our quartz grains? Why do our monocrystalline quartz grains tend to form more of our sand and silt-sized particles and less of our clay and gravel-sized particles? Why are rock fragments and chert tend to be much larger in the gravel and sand size? And why do clays and micas tend to make up most of the clay-sized particles. So we're thinking here not just about the physical weathering processes, but also the chemical weathering processes that we can use to explain the distribution of the chemistry of these minerals and also the size of these minerals. And you should be able now to have a discussion about how we can go from a mountain that's made out of granite with a variety of minerals, with micas and feldspars and quartzes, to get to a beach that's primarily made out of quartz sand. You should be able to explain what happened to the feldspars and the micas and the other minerals that are found in granite that leave us with a beach that's primarily made out of quartz sand.